Hello everyone, I'm Chen Gong, come from University of Virginia, and today I want to introduce a new concept, unlearning in offline reinforcement learning. Actually, there's so many interesting applications for offline reinforcement learning, like the large language model. It can use the RLHF algorithm to train the agent. But in here, this traditional offline reinforcement learning, this agent is different from the large language model. And in here, we hope to train an agent, use a fixed data set here. And this data set is in this form, the trajectories. Trajectories consist of the state, action, and the reward pairs is a sequence. And here it means that in this state, if we do these actions, and we will receive a reward from the environment, and then the environment will transit to another section. Yeah. Why we need to promote the unlearning in trajectories? For example, there are three scenarios. The first one is automatic treatment plans. And in here, we will record some patient-sensitive information. And the second one is vacuum robotics. And sometimes this robotics will remember the sensitive information for a room. The last one is a law requirement. For GDPR, it means that users have the right to delete the data and erase its impact on the agent. So, for the privacy concerns and the law requirement, this motivates us to develop offline reinforcement unlearning. The most straightforward solution is retrain. It's pretty easy and can be a golden line for our algorithm. Actually, it's a reference in our experiments. We can directly drop the unlearning dataset and retrain the original dataset from scratch, right? It's pretty easy, but this is time-consuming and expensive. And sometimes unlearning requests can be made frequently, so how can we develop efficient unlearning method to approximate this process is pretty important. The next solution is fine-tuning. It's also pretty easy and very popular in other fields of dataset unlearning. We can directly drop the unlearning dataset and fine-tune the agent on the remaining dataset, but we know that this process is unreliable, right? The third one is random reward. We know that the agent learns from the reward. So if we put the reward random, maybe for the same actions and the state pair, the agent will be confused. Maybe in here is this reward, in here is another reward. And the agent will think, oh, it's a one actions, it's a one information, and it will ignore it during the training process. But we know that if we make the reward random, it can make the training is very unstable. It's a joke here. Stable and highly efficient forgetting is what we needed in our paper. So we propose the TrajDeleter. In here, I will introduce why the reinforcement learning training is unstable. Actually, we have two functions to train. The first one is a value function. It means that in one state, if we do this action, how many cumulative reward we will receive when the agent be the turbulent state. The next one is the agent. It's a policies. It's input a state and output actions to tell the agent, oh, you should select these actions. And if we train these two functions simultaneously like GAN, this process is pretty unstable. And then I will introduce the objective functions of the offline reinforcement learning. It's a high level introduced. We can put the agent and the value function training together. It means that in each state, we hope the agent to select the optimal actions to make the value function maximize. Intuitive brought the idea from the gradient set from other area. Learn is maximizing, so unlearn is minimizing. And to keep this waste stable, so we should learn on the remaining data set, but unlearn on the trajectory target trajectories is unlearn trajectories simultaneously to keep this way more stable. But a better news is that if we directly use this forgetting training process, it's unstable because we cannot provide a convergence guarantee for the agent. So we introduce the second convergence training. In this convergence training, we hope the unlearned agent to learn the value functions of the original agent or the remaining data set. Why we should do this? Because we have a theory here built from the previous works. It told us we will do this process. The convergence training can make the unlearned agents convergence to the unical optimal function or agent. But it is noticed that here, we should do them separately. We should do the forget training first, and then we do the convergence training. We cannot do them simultaneously. So another question is that if I am users, others told me that I have deleted your target data. How can I trust the thing? How to determine whether the trajectory deleted is unlearning successful? So this is the second part of our paper. We can use the membership inference attack as an auditor like the previous works. Is that we have many shadow agents, and we can ensure that the shadow agent include the unlearning trajectories. But we don't know the unlearning agent is include the unlearning trajectories or not. So we can compare the features between the shadow agents and the unlearning agents to do the decisions. I mentioned before, this stability is a drawback in offline RL training. But a good news here, it can be a tool to improve the auditor's efficiency. How to do that? We can use the unstability of the offline reinforcement training and directly train the original agent on the original data set to do some fine-tuning, and then we can obtain multiple shadow agents. And we believe these shadow models will be different. But for another supervised learning, we cannot do this because the training of supervised learning is pretty stable. And then we can extract the features of the unlearning agent in these features, and then extract the features of the shadow agent and compare the similarity between the features. Yeah, there's so many details here, and I don't want to go in detail them. Maybe you can research a paper for details. Yeah. The final section I will introduce our experimental design. The first one is effectiveness of the auditor. The next one is effective of the TrajDeleter. The third one is the impact of the hyperparameters. And this is our investigated algorithms. And I selected 6 SOTA offline RL algorithms to train the agent. And we use the precision and recall to measure the accuracy of the unlearning rate. And the last matrix is average returns to measure the performance of agent. Yeah, before I introduce the main result, I would say it must our result will be good. Otherwise, this paper will be rejected, right? So I just want to introduce some key insight from our experimental result. Here we have 2 outliers here. We can say in half the chair, the unlearning rate is pretty low, but for Hopper and work 2D, the average unlearning rate is high. This is why, because we find the TrajDeleter may have the difficulty with algorithm when the training is unstable, like these curves. It's pretty unstable. In the worst case, in Hopper and work 2D, the unlearning rates use this algorithm is pretty high, so it's a limitation of our paper, and it's also an interesting future works. I think to develop a more exact TrajDeleter method is the base of the TrajDeleter unlearning, and we should explore more in the future works. The next keynote is that we only used 2.2% time compared to retrain and achieved the similar result compared to retrain. And retrain is a reference, is our golden line. And these tables told us the importance of the convergence training. Without convergence training, we can see here, the remain data rate have a increase. It means that we do the forget training, it will also forget some trajectory in the remain data set. And then without the convergence training, the return means the performance of the agent will have a big decreases. So the convergence training is pretty important in our algorithm. It also highlights that the second point is that in offline reinforcement learning, the convergence problem is always we should pay attention to develop a more stable convergence training is pretty important. The last one, I want to introduce the hyperparameters to say how to balance the forget training and the convergence training here. In this picture, I make the forgetting step and plus the convergence step equals to 10,000. 10,000 is only 1% of the training step for retraining. With this picture here, the forgetting step can significantly impact the unlearning performance, like these curves, the yellow curves. But for the blue bar, we see that the convergence doesn't sensitive to the agent's performance. So sometimes a small value of convergence step is good, and the forgetting step can be large. And in our paper, we set the convergence step is 2,000, but the forgetting step is 8,000 in our paper. Overall, this paper proposed a trajectory forgetting method in offline reinforcement learning, and we hope this paper can bring some ideas for the future large language model training. We know that the large language model using the RLHF and can be seen as the specific types of the offline reinforcement learning. So I believe our paper can bring the insight for this area. And thanks for listening. This is all my presentation.
Thank you very much. We have time for a couple of questions.
Hi.
Hello. Thank you for your presentation. In your experiment that you showed how to unlearn the cheetah, okay? But do you need a shadow agent for each user that wants to be forgotten?
Sure. I think, yeah, it's true. So sometimes you mentioned, so the training of the shadow model is no inefficient, but in our method, we put this way, we can simply to fine-tune the models on the remain data, on the original data set, and we think this process can improve the efficiency of the shadow model training.
So you will need a new agent for each new user that wants to be forgotten, or can you like merge some user together?
Yeah, better together. Okay. Yeah, compare them together.
Okay. Thank you.
Any other questions? Yeah, let's thank the speaker one more time. Thank you very much.
Thank you.